Math.
Okay. So it's like some of us. Okay. One of you can let me know if you have gone through the lecture slides of the week 2. If not, then we'll go into much brief or just superficially through them, just to give you an idea so that you'll be able to solve the assignment. And just to let you know that these assignments are not actually what's there in the lecture sessions. You can get to know about the lecture sessions. There are much more information in it. Assignments do not include everything from them. So if you want to have a much more detailed information for the same, you can go through the references that were tagged in the previous lecture. Link must have been shared with all of you for the same. So there you can access the presentation as well as the transcripts. Also, now all sessions are also available on the NPTEL website for biomedical signal processing. So today we'll start today's one. Let me know if you have any doubts or queries at a particular instant of time. We'll stop through that particular for that like topic. If I'm not able to solve, I'll let you know in the next Tuesday session. Okay. So first, what we'll be seeing in this particular session is that what is actually is like how signal acquisition, data processing is being done, and where actually this biomedical signal processing takes a is like play into this particular system. So we have a particular patient through of whom the diagnosis is to be done, and we have a physician who will do this everything. But we have a system for the same through which we can do this everything. So we have the sensors, then next to the sensors, we have the amplifiers. What are the sensors which will detect those minute signals? It's actually the information that we're interested into that we want to extract. So our sensor would be specific to the same thing. For example, here, if it's a cardiac microphone or it's an ECG electrode to record the same activity of a particular region of interest. Then we have an isolation amplifier unit, that's a preamp. So what does this preamp does? It will isolate your signal from the noise signals. Okay. So we'll isolate the signal from your noise signals and then we'll boost your own signal. Then we have filtering, buffering, amplification stage, and analog to digital converter. So doing this, all steps are even necessary so that the information that you get from your own sensor, that is the principle of transduction, what you sense and then you convert it into the, it's like the electrical form, so that you are able, say you have the actual signal on which you can do the processing and then post processing in order to extract the things that you want. So this is how, this is the most important stage of data acquisition. Say if you don't have your data very accurately, or there's some, it's like most of the noise present in your data, or what you have acquired is just nothing, is not of use to. So what's the purpose of doing this processing and post processing? So first you need to know that what you're extracting, where you're extracting it from, is it appropriate, the amplifier that you're using for it is, and does it have a proper gain, or the isolation amplifier that you're using, is it grounded properly, the filtering that you are applying, is it necessary for that particular analog filter? All those things you need to consider. Even okay. So after the signal data acquisition stage, we have the pre-processing of the signal. So what do we do in this pre-processing is like, we just filter the signal, remove the it's like high frequency data from it. And the next what we do is we extract the signal that is of interest. So what actually is high frequency? High frequency normally represents some noise signal. And then we remove the artifacts from the same. So there are the physiological or pathophysiological or pathological events as well as the components. So say if I'm recording a ECG from a particular patient or a participant, and there what's of interest is that I should be able to see those PQRS waveforms. But then what do I need to do if I have to calculate the heart rate? So the distance in between two R is like R to R interval. But if you say that in between R to R interval, somewhere in between it's peaking very highly, so that's noise. But if a person like me who is just studying this for the first time, I don't know, and okay, I'll say that okay, it came very fastly, so this is R2R. But someone might also say that it's something called as tachycardia, in which the heart rate increases up to 120 beats per minute. So it can be that this R2R is like here. So you need to know that what you're extracting, as well as if it's noise or not, what's the frequency of that noise, or if it's a line supply noise. So you need to filter those all things. So that's a process which is called as pre-processing, so that you get your data ready in order to extract the components that you actually want to do. Then you have post-processing and analysis. So here you extract the waveform or its features, the higher order pattern, classify it, cluster it. So this is all which follows into the final acquisition, and it's like the final part of your data post processing, and then it's being given to the physician for them to make diagnosis of the patient who is being treated or will be treated. So a simple overview for the same is like, if you have a person doing the same things, and you let's say that this is a signal generator, then what it will do is like, will actuate something, will see what the responses are. Okay, it gives back the sensor, and then this is the feedback through which the trainee will get, as well as a doctor, and then will change. It's like whole loops goes on and goes on. In between you have the acquisition, it will change to. So here is how we see that, okay, how the loop actually goes on, or in between the electrical part or the physiological part or the patient scenario, the feedback scenario, everything comes into play. So what we'll see in this slides today is that week 2 is mostly for artifacts removal. So we'll see different types of filters for the same, or we'll see some transforms also. We'll see something related to signal processing, that is convolution, cross correlation, autocorrelation, things like that. It's like simple signal processing techniques. So first here I have dotted out everything in points in this particular lecture slide, so that it should be easy for you to know that how it's been going on, so that you don't have to go through the lecture slides again and again, or the videos recording again. So first, what's a patient as a source of signal? Then what's a transducer? We have to collect the signal. But can some of you unmute yourself and say what is actually a transducer do? It's like convert something to something, but what's that? What does it do?
It converts one form of energy into another, mainly
Okay.
electrical.
Yeah. So what can be potential examples for the same?
Mic that we are using.
Yeah, yes. Then
LVDT.
Nana, yeah. Yeah. So there are many transducers there available which converts from different forms to different forms. So there are again different crystals for the same too, so which are being used in medical imaging in order to as like take the data or convert the data forms into one form to another. So these are maybe are interested into playing in between different types of signals, so hence we convert it. But for playing with them, we need to isolate it so that the electrical potential is not injected back into the participant. So for that, what we need is a proper grounding. So it saves the patient from a high potential. And we amplify the signal, we filter it before converting it to digital, so that we don't actually have the analog or very high frequency noisy signal back to us, which will do processing on. So the focus is after digitalization. There are different types of blocks in it. So the information at the end is given to the physician, which he can understand, diagnose, and give therapy to the patient. So this step is the first step for signal processing. Next, so here you there's something called as a random signal. We'll talk about stats now. So there's something as random signal. So can one of you unmute yourself and let me know that do you know the difference in between a continuous signal, a discrete signal, and a random signal? There's something on the slides too. You can use information from there as well.
Difference between which signals? Actually, I
Uh,
was not able to hear it.
yeah. A continuous signal, a discrete signal, a random signal.
Continuous signal are defined for continuous time, that is on the integers as well as like 0.1 second and like that. And discrete signals are defined at the discrete intervals of time, like 1, 2, 3, 0, -1. And random signal, they are like calculated using the formula that number of turning points should be greater than 2 into n minus 2 upon 3.
Okay, so that's just a criteria. I also got to know about this criteria. But do you think that a continuous signal as well as this discrete signal or analog signal and digital signals, this can be random, or it's well defined that okay, this particular signal is random and this particular signal is not? Someone else can also unmute yourself and let me know.
These signals have a same magnitude as well as same direction, whereas discrete signals are different in their magnitudes and direction.
Yeah, yes. So for a random signal, it's well said that we can't predict it. For other signals, we have a well-defined signal processing techniques in order to we know what characteristic they have, if it's linear, if it's non-linear. We have different kinds of fitting for the same. So random signal can't be predicted beforehand. So there are some tests in order to test the randomness. These are Kendall's Chalice test, Kidney's test, when there's no shape for the signal. So if you see a particular signal, say like this, how do we define a particular signal like this in order to know that okay, if it's random or not? So as someone from the audience said that if the number of turning points are greater than 2 by 3 into n minus 2, so what are turning points is like the time it increases, the gradient or the slope of it increases, then it changes, it increases, then it changes. So these turning points are being defined as a sign of the change of the first order derivative. It's like dx by dt, or it's like just take a slope of it, say y by x, it will give you the gradient for the same. So next we'll be seeing that what's a PDF, that's a probability distribution function, a PMF, a probability mass function, CDF, a cumulative distribution function. So a PDF is like, in simple words, it's defined for a continuous function, not for discrete signal, whereas PMF, that's a mass function or probability distribution function for discrete functions, is defined for discrete signal. So this is how they both have been noted out, and it's like will be followed through the course of this biomedical signal processing. So it's being said that if it's a random signal is given and that's a real variable, so we'll define a PDF for the same for the entire range. But if it's continuous, so it's like for this particular value, the probability is this, then from this to this is like at least this point, at least this point. So it forms a continuous curve. So that is nothing but the accumulation of all the probabilities is like from a negative infinity, is like from wherever you're taking the range from to a particular point, which wherever you're interested into, that's called CDF. So there are two simple useful stats for the signal. First is mean, that's the expectation of the variable, that's just the average of it. Next is the variance, that's the second order change in the moment, that's the deviation from the the deviation of that particular point from the average. So square of the same, that's the standard deviation, and square, that's a variance. So this is how we define these two statistics of the signal. So can one of you say that why is actually mean important? It's like variance. Okay, we all know that if there's changes in the signal, there's some variability in the signal, so we define variance for the same. We also compute some root mean square errors, or accuracy, or say deviation, all those properties. But why is actually mean important? There is a significance for mean of the signal or average of the signal.
Actually, it is useful for calculating the deviation of each and every point from the average value, like the bell curve that we get, normal distribution.
Yeah, that's true, but that's for variance. I was asking for mean. What's the role of mean in a signal?
It minimizes error in the prediction of any one value in your dataset. Means if there are any datasets, if we take the mean, then it has the lowest error in it.
Yeah, yes. So whenever we do signal processing, unless and until the mean has some significance value for the same, we subtract the mean from the entire data set, or we subtract the minimum value as well, so that we don't get the maximum errors, so that we are in the baseline, or all of our data is being averaged to a same reference point. So next, so if you're doing an experiment and you have a particular observation for the same, say I have connected, okay, I'm taking a recording from oscilloscope. I have connected some Arduino, or say some powers. Okay, say I'm designing a power supply circuit for 9 volt or 12 volt, and then I want to see the waveforms from the same into the oscilloscope. I added the cables, connected the BNC cable to the oscilloscope, the crocodile type of cables, and then I have to see the signal response. Okay, are the waveforms gated or not, or are those clipped or not? So at first, what you see is that the waveform comes, it fluctuates, and then it normalizes at the baseline. So the horizontal origin line for the scene. So what we see there, the first is the signal, next is the noise, but both of them are random, because there, if you see it in sample mode, you can see that it's varying or it's fluctuating very nice. It's like very continuously. But then if you average it for n number of times, say in the order of 2 raised to n, so if you average it for n number of times, depending on your type of system that you're using it, you'll see a nice smooth waveform. So this is how a particular observation is being related to. And this type of noise is very additive. So if your cables are not properly connected, or if your circuit has some loose connections, or there's some component that's not working very well, or it has some problems with it, so there would be noise inherent into the system as well. And there are noise added by the humans also. So whenever you perform any experiments, there are noise. But if the noise is zero, or the mean noise is zero, then it's a happy situation. What you get is a signal of interest. So normally how you measure the mean of a particular signal is expectation of both the variables. So it's always additive. It's not a cumulative, it's additive property. So same follows for the variance as well. It's like square of the second order moments for both of them. So this like this way. So here what we see that both of them are uncorrelated. So can one of you say that why it's uncorrelated? It's like why it should be uncorrelated. So just a single hint that one is a signal that we want, and there is a noise. So we want to separate both of them. If they are correlated, then what will happen?
It is difficult to separate them. Or
Yeah.
if we separate the noise, then it can be possible that our signal will also be lost.
Yeah, yes. So hence it's a thing that normally what we assume is that both of them are uncorrelated. So this is additive. If it's not, then it would be very hard for us to separate the signal from the noise. Even if we are able to do, some part of our signal would be lost in the same process. So okay, so so there are two type of averaging here. First is a ensemble averaging, next is the time averaging. Let me pull both of them so that it's very obvious. Okay, so let's say we have a signal that's x of k at the particular time instant of t, where k varies from 1 to m. So I'll just give you a basic definition. Then you have to tell me that what this actually both of them are. So what's an ensemble? So say I'm acquiring something. Um, okay, you all are aware with imaging. Say how do I say? Okay, so whenever whenever you go for diagnosis, a particular physician will come to me. He'll diagnose me for one time. He'll diagnose me for two times. He'll diagnose me for three times. So what he checks at that particular n number of times is that, okay, what's the recording here? What's the recording then? What's the recording at the next instant of time? Is it varying, or how many changes are being coming into it? Or what he can do is that he'll ask me first day, he'll tell me to take some amount of pills for this particular time. Then he'll ask me to come next time. Then he'll ask me to come next time. So there are these two types of averaging. It's like first is ensemble averaging, which says that you average the entire period for n number of times, not at particular instant of time, but for a particular frame. So say if you have acquired something, you acquire it again, and again. You take that particular window and average them everything. But then while you average it, you have to be careful that you need to divide it by the total number of frame, or the total instances that you have by it, or else the mean that you compute won't be accurate. Next is time averaging. Is that if say you have acquired from 0 to 200 millisecond, and you have to take an average of the entire signal, just simple time averaging divided by the entire duration of time, and you'll get the average signal or the mean for the same. But here one thing is that both of them can be same. If it's same, this process is called as ergodic process, is just a name given to that particular process. When it happens, say the duration is exactly the same, the time of acquisition is also exactly the same, or the acquisition of interest is also exactly the same, it would be called as an ergodic process. But they both might not be same always. There's a imaging modality called as Doppler imaging, so in which you take n number of frames so that you know where the blood flow is actually going where. So at first instance, say you took an image, there you also only got that, okay, here the blood was present at this particular instant of time at this particular location. Next you take, it move. Next you take, it move. Next you take, it moves. So this is how I can do an ensemble average. But this time average won't, might not, it's like, it shouldn't, it's like, must not be the same, just because my time averaging this particular limit or the windowing for the same shouldn't be the same. So both of them might vary in that particular case. Next, so there are these two types of functions called as autocorrelation and cross correlation. I'll show you the waveforms for them and then we'll go into the formulas for the same. So here, if you see, there is a signal x of t, a sinusoidal signal, and we have another same signal that's an x of t, but it's moving over time. So if you see, okay, when it plays it again, we'll see. Now, if you have tilted the signal and the same signal is coming at different instant of time, so we see here the final output waveform is being generated. So whenever both of them are same, exactly matching, it peaks at, it's like the amplitude is maximum. So this is how autocorrelation works, like same signal, same, but varying in period of time. But then what's cross correlation is that you take two different types of signal and then you correlate both of them. So here, if you see, there's a rectangular, there's a sawtooth or triangular waveform. And then if you move this particular triangular function, it will be constant for this particular time. And then it will again drop when the second edge arrives and it will start decaying. So this is how these two functions have been defined. But do all of you know that before autocorrelation, cross correlation, what comes? It's like the basic version of both of them. The one that we start learning after perhaps delaying in advance, and then we start into the signals. Okay, if we have two signals, then what do we do? It's like the properties are also different in time domain and frequency domain. If in time domain I do something, in frequency domain they are multiplied.
Convolution.
Yeah, yes. So in convolution, what happens is that you take a signal, you delay it, or you entirely flip it if there's no delay given, and then you multiply both of them. So that way, here the role of sign takes place. You invert the entire signal. But in autocorrelation, the sign went off. So what you do over here is you directly multiply if it's autocorrelated, same number of time. Where it's cross correlated, you multiply it. It's like two different signals at two different instants of time, or perhaps can be same instance of time. But then there's something else apart from autocorrelation, cross correlation, that's called as covariance function. So what happens in covariance function is that you just remove the mean from this cross correlation function. Now, if the mean of both of these signals is 0, which might not be the case, then it will mimic this cross correlation function. So the first thing that we saw, that unless the mean has any special meaning, we always remove the mean from the signal before doing any processing. Okay, so what these definitions fine for all of you, because we'll be having some examples on the same. So knowing this autocorrelation, cross correlation is something you should know. You can give a thumbs up if you don't want to speak. Okay, I suppose that you all of you got the thing, or if you didn't, you can add it into the chat box as well. Okay, so next, so we saw a random signal. The random signal was the one which it varies in magnitude each and every instant of time, doesn't have a specific signal processing technique for it to model also. So we just had the turning points in order to know if it's random or not. There were other tests, but we didn't have much brief about those tests as well. So the other type of signal is the stationary signal. So what's this stationary signal? The signal that doesn't change in time. So what doesn't change in time is called as invariant. That's no variation. So if it's no variation, it gives us no information because the time is not changing. Hence, the statistics of the signal won't change over time. So if it's a continuous variable, the PDF, if it's a discrete variable, the PMF, it won't change over time. And there's also a possibility that this PDF and PMF would be same. Now you might ask that how can a continuous variable's PDF would be same as a discrete variable's PMF? So the thing is, if you sample both of them, if you sample the continuous variable in a way that it mimics your discrete variable, which was supposedly the signal that you were trying to see, then both here, if you map the probability distributions of both of these, it would be not, it's like would be same. So they say that if it's a stationary signal, all the moments are time invariant, but there are also two terminologies for the same. It's a strict sense stationary signal or a strongly stationary signal or a process. So it's very difficult in order to calculate all the moments because you don't have any variation over time. If it might also vary with time, then you know that okay, at this instant of time this activity was there, at that instant something else was going on. Here everything's constant. It can be something like a DC signal, so you don't even know that if it's something going on or not, or are you receiving your signal actually very nicely or not. So there are even some signals which are called as weak sense stationary, in which the first and second order moments are time invariant, which means that if you take the first order moment at particular t1 time, and if you square it and take the second order moment, both of them are time invariant. It gives the same like if it's the difference, it will give you the same function. Or if you take the mean at first interval, mean at the second interval, both are same. So if it's not weak sense, so there is a term given by people who say that okay, if I have a slightest change over a smallest period of time, then I call it as quasi stationary process, which doesn't change over the entire, it's like a smallest period of time, but we can see a very small window, so that it's not that stationary or it's not that weak sense stationary, so I can perhaps try and do some processing on it. So just actually inverted of the stationary process. So here, if you can see, this is a stationary signal, won't change over time, but this is a non-stationary signal, which varies actually with respect to time. Its amplitude increases, drops, like that. So if it's a stationary signal, the envelope would be same. But if it's a non-stationary signal, it would vary and actually peak at particular periods of time. So next we have event-related potentials. What's actually this event-related potentials? I guess we saw in last Tuesday, but we saw something called as EEG, which gave us a field potential at a particular location wherever you insert those electrodes into. Now, these electrodes were disposable surface electrodes or needle electrodes. So what you actually do is like measure the brain activity. So this is how a ERP looks for actual brain activity response. There are different components for the same. Different components tells us okay how the activity is being going on with respect to how the signal processes over time. So what these people in cognitive science they do is that they process this actual potential waveform, but you know what, most of the time this waveform isn't how it's actually shown to us in most of the books, or it's not this significant. So you actually need to see that which particular activity, say if there is a P1 or a P2, if it's related to a sensory information, or if it's related to a perception or say tactile features, all those. So for them, then you need to see that okay, when my waveform is giving me a peak is positive, or if it's a negative, what's the pressure at that particular peak, or how much dip is it's giving, how what is the what you say the width of that particular peak. So from there you get to know that what all differences are. So this is how event related potential is being defined. So now from we'll see that what are the actual problems in our physiological signals. So why do we actually need to remove these artifacts? So we had this EEG signals. Now we saw in last class that these EEG signals are very noisy. You can't actually see the alpha, beta, delta, gamma very nicely unless you know that which particular frequency band that you are looking into. So there's noise in these signals. We actually listen to the brain activity actively or passively. Now, how do you listen actively? Is that someone is playing it for you and then you are listening it. Or how it's passively is like someone else is doing the experiment and then you are listening to it, but you are involved in some other experiment. And there's something going on in between. It's like you can't actually isolate yourself for this particular experiment, and you can't force your participant to just see over here. That's why people who do cognitive science experiment, they have a properly insulated, very shielded rooms, so that the participant is just focusing on the experiment that they are doing on. So there are something called as rare tunes, frequent tunes. The counts of them also differs. It starts when it's played as well. So there a person has to listen, distinguish, and then count. So these are how the signals are there. It's like the problems are there when a person does something acquisition of EEG signals. Then we have ECG signals. So as we saw that, okay, if there's high frequency signal, we can't actually differentiate in between the higher peaks or slower peaks. If you see over here, okay, there's it's very evident that, okay, this is P, Q, R, S. But there's also a line supply noise that's of 50 hertz. If you're here, it's 50. If there we are there out, it's 60 sometimes considered. So we normally use a notch filter which removes a single frequency component out from it, and we subtract it. Not actually subtract, it's like just remove the signal from there. So okay, so if this is a high frequency, so there are different kinds of noises. This noise, like noise can also come from the electrodes that you're connecting it. If the electrode connection is not proper, if you just tilt it a little bit, the noise would appear into your signal. Especially this electrophysiological signals, these are very sensitive. Also the electrodes for the same are very sensitive. If it's not very properly connected, or there's this electrolyte gel which matches the impedance of the like the electrode to our own surface body, so there also it gives the inherent noise from the same. And this line noise, all this low frequency noise that's for the baseline drift, it might also come. So what you need to do is, like, you have to apply different kinds of filter. You need to identify where the particular noise is being interfering, what information that you need, and then filter it. So this is how there are problems in ECG signal. People have been working on the same. There are lab view models working on. People make lab. It's like I did in my bachelor's. I did a project on LabVIEW where I acquired this ECG signal with LabVIEW DAC system, and after which we characterize the different kinds of arrhythmias. That's if it's a brady, if it's a tachy, if it's a flutter or flit. So all this we differentiated, and we saw that, okay, how to do the signal processing, filtering, and acquisition. So what all we saw till now, we saw everything in time domain. Like, we didn't convert it actually into frequency domain. So what are the advantages for time domain? It's like it's very faster, but the spectral information of the noise is not required. What's the spectral information here is that the magnitude and phase of the signal. What we do is we take the voltage versus time, we find the peaks, or we take the average, we do the statistics, and that's it, we are done. But what's the disadvantage? We don't have a control of the smoothing that's being done. It can be over smooth or it can be under smooth, or the sampling might also vary. So these are the disadvantages that we face with time domain filtering. Next, there is it's like some averaging was left in the time domain filtering. This is also following into the same domain. So one is synchronized averaging. So what happens in synchronized averaging is that, I hope you remember what we saw in ensemble averaging. Can one say just the difference in between time averaging and ensemble averaging? Let's go. We have assignments to solve today also.
Ensemble averaging is for particular frames we are doing, and for time averaging we are doing for a particular time period.
Yeah, yes. So what happens in synchronized averaging is that, okay, if you have used an oscilloscope perhaps, so I'm sure you all might have used an oscilloscope to see the readings. So what we do is that there's an option called as trigger and then sync it. So what the sync does is, it makes the different kinds of circuits that you're playing into role in, it makes everything to start at t equals to 0. So that it's not that, okay, my Arduino started at some t equals to t1, something else started at t equals to t2, and now you're acquiring something, and there you need the time axis, which is actually a lot of interest for you, and you need to know that how the waveform varied or what's the drift for the same. So for that, the synchronized averaging was being used. So we take multiple ensembles also for the original signal, also for the noise that we are looking into. But if it's zero, the zero mean noise, then what it's actually is the m times of the signal that we are having. That's the weighted average of the signal that we have. So for this, what we need to do is that we need to align the signal properly to get this. Like just see all the connections are very done properly. You have your electrolytic gel connected. So depends on the type of system that you're playing into or the type of application that you're going for. The SNR for the same is computed as square root of m times the SNR of the signal that you are playing. So here, it's like you can see that. So how do we do the synchronized averaging or this ensemble averaging? Is that you take a particular signal n number of times, do multiple realization of the same, find a reference point, align all of them, and then add them. But after adding, you actually need to divide it by the n number of realization what you did, so that you get actual average. But instead, you don't get just the addition of each waveform, so that it will result into something like this. But whenever you divide it, so you get a actual synchronous averaged or time averaged waveform. So which actually from here you can actually see, okay, what are the peaks, what can be the pressure at this particular peak, or if I'm for ECG, let's say the same R to R interval. Now, can one of you unmute yourself and say that if it's like if I'm doing some signal processing, now this one also gives me some good distinguished peaks. So why shouldn't I use this one peaks, or should I use this one, or should I always use this one or not this one? Just a random guess.
Maybe there is a time when you get confused in one of the point.
It's fine. Someone else? So it's very
I think
obvious
we
here.
should use.
Yeah, yes,
Yeah,
yes,
I
go ahead.
think we should use the highest peak.
True. So what happens is that, say you are calibrating a system. Okay. So what calibration means is that you need to get the ideal parameters. Obviously, that's not possible, but the parameters that you will, it's like if you plug and play the system, you should know that what are the properties of the system, which came along with the manufacturer's manual. So you calibrate a particular system using the ideal systems that are available in your laboratory. So when you do that, you get some waveforms for the same. Say if I vary the intensity, I'm taking some measurements via a precise fine needle system, and then I'm getting some waveforms. Now within those waveforms, I won't always consider the averaged plot, just because this average plot will give me the averaging of the signal, of the noise, or of the drift of the signal, which varies over a period of time. So what people, or like whenever we do this signal processing, when we are actually experimenting, we always take the sampled waveform. So what we get in the sampled waveform is like we get the highest peak, but we won't get the peak which is being added or being averaged after being considering the noise as well, because here we aren't separating it from the noise. This is actually from the oscilloscope. So we always save this waveform and we find the maximum peak of this particular waveform, and then we process it further. Okay, so this was all about ensemble averaging, time averaging, and then what was the last one? I guess synchronized averaging. So next, something called as moving average filters. So for this one, it's like I suppose that you know something about Z transforms. So this is nothing but if you have a particular system which is being realized by some delays, then that particular systems, if we take the weighted average of those delays, and find the transfer function for the same in this form. There's a transform called a Z transform, which helps us to modulate the transfer function for the same, and to modulate this what do you say, the poles and zeros of the system. So it helps us to make it very easy. So there are two types of filters for the same. One is IR filter, another is FIR filter, where FIR stands for finite impulse response, IR stands for infinite impulse response. One needs a feedback, one doesn't need. So here what we do is like, so there was a problem in synchronized averaging, is like every time you need to see that everything sync in between each other. So that might not be the always case. Okay, so if you have a system and that system doesn't have a trigger with it, So how do you sync it with your oscilloscope or say any particular device from which you are taking the reading from? So this will always play a problem, or there would be some problem for the same. So what you do is moving average. You use a moving averaging filter. So you average it over the entire period of time, and you differ is like change your windows from this instant of time to other instant of time. Now you might ask that, okay, this is different from the time. It's like this is mostly similar to the time averaging filter. It is, but here we don't actually take the realizations at a particular window of time and then we divide it. However, what we do is like we take it for some plus more period of times, like advance the signal or extrapolate the signals like from this particular points that I have, and then I take the average for the same. Again, it works with a single input. It doesn't need the input again and again. Multiple realizations aren't needed. It's suitable for a real-time operation. So this is how a particular signal over here is being given to. So this is it's like how do you realize this particular system? So say I guess it got cropped up, but say if I have x of n as a signal over here given, okay, so this x of n is weighted by b naught and then it's added, multiplied by this particular delay and then weighted by b1, similarly multiplied by this 2 b2, and it goes on and goes on. So how do you realize this particular system is that bx, that is the number of weights that are given, where x varies from 0 to k, times x of n minus k. Why x of n minus k? Because there are being delays that are being added over here, where if it's x of n, it would be 1, z raised to 0. If it's x of n minus 1, it would be z raised to -1. So this is how we say. So that's nothing but addition of the present signal and the past few samples of the signal. That's a weighted average for the same. So if you convert it into z transform, that is y of z, and that would be x of z, or and then this x of n minus k becomes z raised to minus k. This is b of x, so we convert it into b of k, and then you divide y of z by x of z, you get this transfer function, which is being defined like this. Now, if you give an impulse, what you get here is an impulse response for the same. So this is how for each and every system, when you calibrate it or find its a response function. So first of all, what you do is like you find the point spread function, and that point spread function is defined by the impulse response. So this impulse response tells you what the system's resolution is, or how much you can actually differentiate in between two different periods of time, or at a particular location also in between two scatterers. So this is how it plays a role in. So the same thing that we saw there, that it has finite number of terms. Initially, for simple scaling, we take b naught is equals to 1, so that it varies from 1 to 10. This was a type of finite impulse response. You might have seen that there's no feedback that is given back. So it's like from the output y of n. Okay. That is from the output y of n, we aren't giving anything into the input over here. So that's a simple realization system. We need not need to worry about the stability of the system. It's the filter design is relatively very easy. Okay. Again, if you see over here, this transfer function, if I do b of k divided by z raised to k. So do all of you are where it happened? Okay. So everyone is aware of poles and zeros.
Yes, ma'am.
Yes.
Yeah. So what are poles when it is 0 or when it's infinite, or what are zeros? It's evident from zeros, but what are poles then?
When the denominator of transfer function is becomes 0, at that value, it is called poles.
A pole. Yeah. So over here, if you see, is there any pole b of k by z raised to k?
Z equals to 0.
So only at that particular point, but apart from that point, we do not have any poles in this particular system. So again, it's being taped by a particular delay. So this type of system is called a tape delay system. And if the weights are chosen properly, it can also be symmetric, anti-symmetric. So the linear, it's something called as linear phase. It's important for the sensitivity of the signal. So there are some kinds of delays. So delays can be modulated in a way that they it's like form a triangle, or it's like delays are modulated in it's like some other point of in which these filters are being named. So there's a Hanning filter. It's also called as a triangular filter. So the simple analogy is that the weights are like triangle. It's also called as an integer filter. So if you see this system, How do we define it? It's like x of n that's being multiplied by 1 by 4. So everything's multiplied by 1 by 4 here. We take it out. Then we multiply this x of n by z raised to minus 1. Then okay, so then okay, so x of n times z raised to minus 1 times half, then plus of this x of n times z raised to minus 1 times 1 by 4, and then we add all of them. So here, as I said earlier, that if the input given is the impulse, then the output would be the impulse response for the same. So just represent differentiating this x by delta. So what's the only property of delta function where it's 1?
At 0.
Yeah, so if this particular function I'm defining at some other point, it won't give me any value. That's pretty obvious. But what happens is that if you have two different delta functions, the property, say it give, if say this particular delta of n minus 1, and also there's a different function called, say if there's h1 of n, there's h2 of n, if both of them are added, the delays of them would be added. So it would be like n of h plus k, or some other values would be added in between. So same, I guess it's a continuation for this one. Okay. So if delta of n, we have plus 2 times delta of n minus 1 plus delta of n minus 2. So this delta of n, or say this x of n, it would be easier from here. So if this is z raised to, you take x of n out, this is a delay over here. Here's a delay of 1, delay of 2. So how do we write it? It's 2 raised to z raised to minus 1, z raised to minus 2 plus 1. So this is actually the square. Now, if I substitute z is equals to e raised to minus j omega t and t is 1, I get this particular waveform. And if I convert this, it's like take e raised to minus j omega outside, I get this, from which I can compute the magnitude and phase for the same. So how we compute the magnitude is like take the square root and square of them and phase from this particular it's like exponential term. So a simple example for the same, if it's defined, say from k equals to 0 to 7, hence dividing by 1 by 8, that's the average, and x of n minus k, so it would be z raised to negative k, and then we have z is equals to e raised to j omega t, t as 1. I'm just telling you this because in the examples there are some questions like for this, so you will be aware of it. That's why. So if it's a moving average filter to integration, so how do we integrate it from t1 to t2 of x of t of dt? But if it's a causal signal, so okay. So can you say what's the difference in between a causal signal and non-causal signal?
Causal are defined for the right hand side and non-causal are defined for LHS as well as RHS.
What's anti-causal then?
It's only defined for the LHS.
So same as you said that for causal signal, it's always the positive side. So general form of signal would be take it from negative infinity to the original time instant that you're like the time point that wherever you're looking into. So again, if okay, so if we have y of t is equals to from t1 to t2 in a normal general form, x of t dt. So if we take the frequency domain or say the Fourier transform for the same, if it's differentiated, it would be j omega times of it. If it's integrated, it would be 1 by j omega of it, x of omega, and this is followed by this dc term, which is like it follows from the duality property that pi times x of 0 times delta of omega. Wherever this value is 0, sorry, wherever this function is 1, it would give a value for the same, hence it's 0 and this is delta of omega. So again, the magnitude for the same would be 1 by j omega, sorry, no, not j, but okay, 1 by omega, and from this j we'll get the phase for the same. That is, if we take this j upward, it will be negative j, and it will give the phase of negative pi by 2. So time domain filtering done. What's in frequency domain filtering? Frequency domain filtering, what we do is like we either convert it into Fourier transform. So there are different types of Fourier transform. There's the fastest one that we know is the fast Fourier transform, but this fast Fourier transform also came from discrete first, like discrete Fourier transform, if I'm not wrong. So I guess it's discrete Fourier transform. Okay. So what the main thing in between there was the storage was an issue, as well as a continuous signal was an issue. Hence, whenever we do this processing, we always do fast Fourier transform. There's not actually a function available to do DFT of a particular signal. So again, this saves discrete into discrete, and hence it's more faster to store also and for the processing also. Again, the artifacts that we see in our original signal are normally repeating after a particular instant of time to next instant of time. So those are periodic artifacts. So it's very simple. A block processing is being done, and a frequency component by 0 or average, you can just calculate the particular component wherever it's giving a particular value. So just find this particular filter, whatever you're doing into, what kind of analog filter you want to apply it into. Either you want to convert into this Laplace domain into Z domain, or you have to be into Fourier transform domain. It's actually up to you. And then just design a digital filter. Now for this type of digital filters, there are some common filters that are being used or that were introduced into the session. Those were notch filters and COM filters. So for them, this is how the poles of the systems are being given. It's like the formulas were the same, that is 2 pi f naught by fs, and COM filters were the same. So can one of you unmute yourself and let me know that what's the difference in between a notch filter and a COM filter? You can also say how it looks like. That's also fine.
Notch filter looks like a notch actually.
And what does it do? Someone else?
Allows only a particular frequency to pass through it.
Yeah. And a COM filter? You can also Google and let me know. It's fine. So COM filter is more like an train of impulses that are going through. So many impulses at this window, other instances at this window. It's like that. So here the poles of the same are being defined. Remind us, like keep in mind this formulas, because they might have been asked into the exams, but there are the sames are there into the assignments. So now we'll go into the assignments then. So we'll do it like last time. One is like we are 11 of us are there. We'll answer is like one by one, or whoever unmutes yourself and can say the answer. First question, which of the following is a transducer?
Microphone.
Yeah, that's true. Why a microphone? You can just say that what's a transducer and what it converts, like which signal to which signal.
It's converting voice signal into electrical.
Yeah. So that's more of an acoustic signal. So it will speak into an electrical energy. Okay, next. So it wasn't there into the slides, but if you don't know, I'll let you know the formula for the same. So can just try. What's the minimum number of bit an ADC required to have a resolution of 10?
4.
How?
2 to the power 4 is
2 to
16
the
and 16
power
is
n.
later.
So it's 16 minimum we need. So hence 10. Okay. Next, what's the resolution of an 8-bit ADC for the input range of 8 volt? So this is resolution. See, we have a voltage also, we have 8-bit ADC also. We always take terms. So whenever we compute this n number of bits, we always take it from 0 to, we always say, if it's an 8-bit, we say 2 raised to 8, that's 256. But whenever we place it in number of levels, that's a resolution. That's from 0 to 255. So whenever we define resolution, but it's again for this particular input range, how do we define it? So something's the output and something's given as the inherent property. So that would be a ratio of both of them.
3.13 millivolt.
Yeah. Yes.
Option B.
This C.
Oh, C.
So voltage divided by 2 is 3. Okay, so this was there in the slides. What's the test for randomness of a signal given by Kendall, Charles, and Kidney for n-point signal?
B option.
It should be greater than 2 times n by 2. Yeah, I guess. Okay. So here, From here we'll start solving, but if it's like if you know, you can just let me know or I'll skip the question. So for a signal x of n 1 2 3, the non-zero minimum value of normalized autocorrelation sequence will be, so negative 1 by 2, 0.21, 3 and 1. You can just let me know that how do we compute autocorrelation. We saw the formulas for the same, but those were just expectation of two signals. But actually, how do we compute autocorrelation? So you know how do you compute, what do you say that, convolution. So it's very similar to that, but we don't have a sign there. Anyone know the formulas for that? How do I open? Share. Oh, okay. Okay, so can you see the whiteboard that I'm sharing? Guys, oops. The whiteboard is visible.
No, ma'am.
It's not visible. I'll share it again then. Oops. It's visible now. Oh, what happened? Okay, close. No, nothing's there. So the slides are not visible now, right? This is visible. Hello. We'll finish it as soon as possible. If you, some of you can unmute yourself and let me know if it's visible or not. Are you facing any issues? It's like you can just see in your this meeting settings if the my whiteboard is being shared, and then you can just go there. It's like for me in my both devices it's being visible, so I don't know if you are not able to see or not. Okay, so I shared it again. Is it visible?
No,
Huh?
it's not visible.
Sorry. Okay, okay. So the question was for auto. What happened?
It is showing this organization only allows members to participate. Whiteboard is in progress.
Is in progress. Okay. Let
Yeah.
me know when it loads.
No,
It's like
it is not loading. It is giving error that this organization only allow members to participate.
that's because that I don't want you guys to write on the micro whiteboard. But okay, wait. Let's see. Hola. Okay, is it there? It's for the first time, hence I'm facing these issues. Okay, wait, what we'll do is I'll shift the control from one device to another. Just 2 minutes, huh? Okay, instead whiteboard, PPT is visible now?
Yes.
Oh, what was that? Okay. Join, transfer to this device, leave the meeting on when you're there. Okay, am I audible?
Yes, ma'am.
Yes.
Okay. Let's try opening the whiteboard again. Now it's visible? Whiteboard's visible now? Okay. I guess it should be visible now. Is it visible?
No, ma'am, it says the same thing. The organization only allows members to participate.
I'll then wait. Sorry for the trouble. I'll share something else then. Share screen, share video.
Ma'am, in our case, the problem is different. It's showing can't show this content. Sorry, you don't have the access, and all the buttons are disabled. Like switching the microphone and camera, each and every button is disabled when you share it.
Oh, okay. What can we do? Can open and PPT and share it then. Because it's like this sums, if I don't try and show you, it would be different then. Okay. Me too.
A better idea is there that you use the drawing tool of your computer or the
But
desktop, whatever you are using.
that's it. I was just trying to connect it to my pad, but when I'm sharing it with my pad, it's not loading properly, or it's like you guys are not able to see. That's the problem. Wait a second. I will share something from here. Let's see if it works. Can we do one thing? I'll share. Sorry. Hello. Okay. Can we do one thing? I'll share a Google Meet link in the chat box. You all join that link. There it will be easy to edit, or I'll just directly share my notes. Will that work?
Yes, ma'am.
Yes, ma'am. Better solution.
Thank you. Thanks for coping up. Next time I'll come up with something else. Are you able to join the link that I shared in the classroom? Sorry, in the chat box? Or is it not allowing you to add there or join there? Am I audible? Sorry for this time. You're able to see the link, right? Or do I post the link again?
Ma'am, where is the chat box?
You
Ma'am,
cannot
chat
see?
box.
You can't see the chat box as well?
No, ma'am.
Chat box is
Okay. Then we'll have to try something here only.
Let's make a WhatsApp group, ma'am. That's a better idea.
That's nice idea, but NPTEL doesn't allow me to do that, right? That's why. Okay, we'll try once more. If it doesn't work, next session I'll show you what's happening, what's being shared. Okay, you can see something?
Yes, ma'am.
Yes, ma'am.
Okay, so can you see that something now?
Yes, Samsung theme.
Thanks for confirming. Okay. This is visible, right?
Yes.
I suppose that should work for today. Let me know if the font size is not proper. How do I minimize it? Okay. So you all remember the question that was given? It was we have to find, okay. So not about the finding, but what we had to do was, the sync is not good. Okay. We needed to do the autocorrelation. So I asked that if you all are aware of how we actually compute this autocorrelation, was that if you have two particular signal, autocorrelation of a signal is defined by Rxx of this, where it's on the particular variable of L, say. So you can just zoom in your screen if it's not visible for you. Okay. So, or do it this way. It comes the full view, right? Huh. It's visible now, abhi अच्छे से?
Yes, ma'am, better in
Yes.
landscape mode.
Okay. Yes. Okay. So the formula for the same is given by n equals to negative infinity to positive infinity of our signal times x of n minus L. So here, this x of n is the signal at that particular instant times of x of n minus 1 is when the signal is being delayed, and then we multiply both of them. So if you remember in convolution, it's just the same, but there you flip the n minus L this term also with respect to the k term that you're adding. Okay. So here how there's something, a property which says that how many number of terms you'll have in your correlation, say convolution or correlation, says that n plus L minus 1. So the number of terms will you be having in this total is defined by this n plus L minus 1. So this L particularly you can, it's like vary, but this n actually depends on the amount of signal. So here our signal of interest x of n is given as, I need to see the question. 1, 2, 3. Okay. And what it's being told to us is that we need to find a non-zero minimum value. After doing this normalized autocorrelation. So what do we do is that first, non-zero minimum value of what? Of the normalized autocorrelation function. So here the term normalized autocorrelation. So how are we defining this normalized autocorrelation? Is that by this? Similar sums are being given for this year's assignment. So you can just try and replicate the same things there. And divided by when the signal is not moved or shifted. So that is by Rxx of 0. What that means is here you add L is equals to 0. So this is just x of n times x of n. Okay. So this one. So given the value for this. And how this particular signal would be defined is that, so for that, okay, so you are now delaying your signal, this x of n minus L. So this n can be delayed till, say, first can be 0, can be positive 1, can be negative 1, can be positive 2 or negative 2, and so on, till which the point would be 0. So say if you have a particular signal, you kept delaying it, delaying it, delaying it, delaying. So now if the signal is coming from this point and the original x of n, this one, which you are multiplying, it is from here. So whatever you do, you delay it. Now the signal is here and the signal is here. The multiplication of both of them will give you 0. So that's the point where you stop delaying your entire signal and you just see, okay, from where the signal would be given. So for this signal, that is 1, 2, 3, you see that is n equals to 0 here, where it starts from, n equals to 1 and n equals to 2. So if you delay it by 1 and 2, you will get, okay, that's a sufficient amount and you shouldn't go more and more iterations for the same. And what is n? N is equals to this, the same values that we had, that is 0, 1 and 2. So for the same signal, our x-axis of L here. So if you just compute it, so now if we do for this r x-axis of 0, this one, that was multiplication of the signal by itself. So that's 1, 2 and 3, 1, 2 and 3. So it's like at once, so just multiply both of them. So that will give you this Rxx of 0 as probably 149. So that's 14. This one. So you just multiply both of them. And then for this one, what you need to do is like shift the value. Now here, this varied from n equals to negative infinity to infinity. So for us, the limits would be 0 to 2, so that it will vary from n equals to 0 first, then n equals to 1, then n equals to 2. So you add these values and then delay it. Say first you didn't delay, so that value we have. Next you delay it by 1, multiply both of them. Next you delay it by 2, multiply both of them. Delay it by 3, multiply both of them till the value gets 0, and add all of those. So if you all are doing this particular sum, can you please do the iterations and tell me? So one simple thing would be that just tell me how many terms would be there in our this autocorrelation. We had n equals to 0, 1, and 2. L would be also probably 0, 1, and 2, because after that this term would be 0. So we won't get any values there. So what is this? This term? What's the value for this?
5.
Yeah. So the number of terms we'll be having in our sequence for autocorrelation would be 5. And when we divide all of those sequences by 14, it would be normalized autocorrelation. So one of you can try for delaying the signal by 1, by 2, and by 3, and let me know what the values would be. We can just try for any two and we'll go to the next sum then.
Ma'am, I have a doubt.
Yeah, yes.
Ma'am, correlation is defined as measure of similarity between two signals. So
One.
if we are taking
Yes.
So if we are taking a non-shifted version of the signal itself, then it should come 1, because correlation varies from -1 to 1 and positive correlation is +1. So answer should directly come 1. Then why we are calculating it?
So it will give you the maximum value of that particular signal. So since this is autocorrelation, if the signal itself is imposed on the same signal, then the value that you'll be getting is not 1, but the maximum point of these two signals. It's like where this signal would be maximized. Got my point? It's like we just see that the amount of relations, like how both of the signals are related to each other at these instants of time. So for that, it's like change the time, delay the signal, and then see the values. You got my point, or was I not able to understand what you're trying to say?
Ma'am, we are trying to calculate the correlation coefficient or the point at which the signals will be maximally correlated, like this.
Okay, just tell me what's the difference in between both of them.
Correlation coefficient is like the indexing, I don't know much about it, but I know that it varies from -1 to 1. If the signals are same, ditto signals are there, then it's 1, like that.
No. So there's nothing as such as correlation index or so. So normally, how do we define two signals like the GIF I showed you previously? So if you have a sinusoidal signal going on, there's some other signals also going on. The maximum response of these two signals, when we correlate the same signal with its own signal, would be when the exact signal matches on it. So if my hand is there, if I invert my hand and match it on, it won't give me the same response. But if I invert my hand in the same way, but there's a thumb over here and thumb over here, I'll actually get some minima. If I do both of them in the same way that both are correlated, like both have an identical, all features are matching, then that's the point where the signal would be maximized and we'll say that the correlation is there. Hence, this particular two signals are correlated to each other. So there are just two different terminologies for the same. One is auto, other is cross. One is with the signal itself, other is one some other signal. It's like with like this or with like this. So those are the only two differences there. It's very similar to how you do convolution. So just you delay the signal and find the points for the same. It's not like computing the index for the same, but you just need to find that at this particular instant of time, what would be the maximum value for the same. Was that fine? Okay, did someone try for n equals to 1? Sorry, L equals to 1? Then we also have for -1, -2, -3.
For L equals to 1, is it coming 8?
L equals to 1, yeah, yes. So you got now, right, how to compute this. Someone else also can give a thumbs up to see it's like if it's fine. Then we have other one. Okay, so I'll go to the next question then. So the next question is for the cross correlation.
Ma'am, what are the options? Can I see that again? Of the question that you have given.
So for that I have to share my screen again. Okay, wait.
Oh, just write it. I will see.
You have to do is we complete the
B.21. Yes, ma'am. It's coming.
task. How do I share it again? Okay, wait. I was here. I shared via here. Oh no, it's actually easy. Share my screen. Ah, it's visible, no?
Yes, ma'am.
Yeah. So the next question is to compute normalized cross correlation in the same way. And there also we are trying to find the minimum value. Normalized cross correlation.
Ma'am, one more doubt.
Ah, yes, go ahead.
Ma'am, in this question, we calculated a single value for the normalized autocorrelation. But the assignment that is given to us, in that we have to calculate a full discrete values.
That's what we did here, right? So we computed it for 1. Now you can compute it for 2, for 3, -1, -2, -3, also 0. And then you can see that how the signal is getting. So you'll get total 5 terms given that for n you have 0, 1, 2. For L you have n number of time till you get the value as 0 once you delay the signal. And that would be number of terms that you'll be getting. When you normalized it by the value at the maximum, that's the 0, Rxx of 0, then you get the number of terms here.
And ma'am, the values for the L are 0, 1, and 2.
No, so what L is actually, L shows that the amount of delay you can give to the particular signal is like till the point that you get some value. After a particular point in which you get 0, that means that these two signals are not correlated now. So there's not much more of a meaning if you just keep on shifting the signal and signal. So you will always get 0. The thing that I stated here is like you'll just shift it till the point that you get something. After a point when you don't have any regions of overlapping in between these two signals, you'll everywhere you'll get 0. So this value is just where you define it by yourself. You can vary it actually. It's like within the real-time axis.
Ma'am, can n be negative like -1, -2?
It can be. We define it like this. Okay.
Yes, ma'am.
Yeah. So next question is for normalized cross correlation. The formula, I'll give the formula and then you guys can do the sum. So here, so what's cross correlation was in between two different signals. So how do we write it? Is like similarly n equals to -infinity to +infinity, and we have x of n times y of n minus l. Now you might say that why always this particular signal? You can actually flip both of them. We can also write y of n and x of n minus l. So it's like both associatively. So the cross correlation for the same, you compute it as r of xy. So this is normalized cross correlation. So you compute the cross correlation of both of these two signal, and then for doing the normalization, you divide it by the autocorrelation of these two signals with each other at their own 0 point when you don't shift both of them. So for computing this, well, you actually use the previous formula, this one, and this one. Okay. So I'll show you the question. Okay. Normalized autocorrelation. Okay, this one. Okay, we don't have to compute minimum value here. It's just the terms. So we can, okay, let's start from how many terms will we have in this series. So we have 4 here, we have 4 there. 1, 2, 3, 4, 5, 6, 7, 8, 5, 4, 5, 6, 7. How many terms will we have over here? So 3, 4, 6, 7, 4, 7. How many? It's like 7 or 8. So from there also you can, it's like
7.
itself.
7
So
terms.
I guess all of them have 7. I thought this was 8. Okay. So someone can try with n equals to 0 and someone with n equals to 1. Sorry, L equals to 1 and n equals to -1. So I guess from there itself we'll get the answer. Okay, so let's try with Rx, this particular value. Just let me know what these two values are. So when we multiply 4321 by 4321, 8765 by 8765 and add all of them. We do this times x of n times x of n and y of n times y of n. Just tell me these two things. At n equals to 0. Sorry, not at 0, but L equals to 0. Where this was n minus L, so L equals to 0, hence n. Okay, here. Here, there.
Is
Let's answer.
Rxy of 0 is coming 0.96? Means the zeroth term of the normalized cross correlation.
I will cross check. So if you take from -1 delayed, where will be the 0 term? On the 0.97, I guess.
What? Point?
9. The screen is not visible. 0.97 perhaps.
Means it's approximately 0.97. My answer is coming 0.9688 something. So 0.97.
Yeah. And the values are this at 0, 0. You computed, right? The normalized one itself.
Yes, ma'am. Our XX0 is 30 and our YY0 is 174.
174, yes. So here you can see the solution also.
Ma'am, your voice is not coming.
Am I audible now?
Yes, ma'am.
No, now you guys are. Am I audible now?
Yes, ma'am.
Okay, okay. The screen is shared, right? You can see the screen?
Yes, ma'am.
Yeah, so the answer for the same is weak and stationary. That was in the slides. So next question. So DC gain of a moving average filter is defined by h of z. That's
3.
1 plus. We gave the answer itself. Yeah. Okay. Can you explain how? By
Putting z equal to 1.
z equals to 1?
Yeah, or adding the coefficients.
Yeah, that's the appropriate way because z is not 1 actually. So like, okay. So next question, the transfer function of a 3-point moving average IR filter is given by which one? So for this one, we actually, so what we saw in the slides was how would
A
we
and
find
D
the
because वो mathematical imprint. If we solve the D option, then we will ultimately get the A option only.
Yeah, yes. So what do we do for that? So we have a signal y of n. You take x of n, you delay it once, you delay it twice, and then you take this, it's like delay it once again. That's y of n minus 1. Take the difference of both of them, convert it to z transform. So you'll either get first one or you'll either get the last one. So last question. So a comb filter is used to remove the power line artifacts at 50 Hz, 150 Hz, and 250 Hz from the biomedical signal sampled at 500 Hz. Which of the following is not a location of zeros in the transfer function of the comb filter? So these are the locations of zeros that have been defined. And I guess I gave you the formulas for poles and zeros previously. So if not, you can have a look. This one's. So what we have now is the comb filter. So the formula we'll be applying is 2 pi m f naught by fs, where f naught is the center frequency or the frequency at which it is being derived on, and fs is the sampling frequency. So here. So sampling frequency, you know that fs is equals to 500 hertz now. How do we write it as 2 pi n times of f naught by fs? Now the zeros will be defined as e raised to j theta n, where e raised to j theta n, how you know is that using Euler's rule that we write cos theta plus j sine theta. So we'll vary the theta that is from theta equals to 1, theta equals to 2, and theta equals to 3, where it's from this 50 hertz, 150 hertz, and 250 hertz, so that you'll get different values of this theta for different frequencies. And from there itself, you can compute the zeros. That's e raised to j theta. Who joined up here? I'll give it the answer this way. Okay, so that way we can compute the zeros. So can one of you try doing, it's like, you know, right? How do we compute the zeros? Was I able to say what you have to do in this question? Did you understand?
Yes, ma'am.
Yeah, so it would be just do it for a single theta so that I know that, okay, it's fine. And then you'll be able to find which one is not the zeros, like not the location of zeros in here. Did others understand? So if you want, I can show you here. So the zero of a comb filter is given as e raised to plus minus j theta n. So this theta n, as we saw in the formula, it's given by 2 pi m f naught by fs, where this is the center frequency and this is the sampling frequency. Okay. So from this one, you have a different values of f naught here when it's derived at 50 hertz, 150 hertz, and 250 hertz. And the sampling here is, I guess, 500 hertz. So what do you do for the first one? Say m equals to 1. So you have theta 1. You do 2 pi f naught, say 50 by 500. Find the value of this, convert it into e raised to plus minus j times theta n. Now what this is, using Euler's rule, like this.
Can I have a look on options, please?
Yeah, sure. So the options were, it's like you can say which one you got. Who was the one who turned his mic on?
Sorry, my mic is off. For 250 hertz, I'm getting -1 plus minus j0, and
Okay.
for the second 150 and the 50, I got the real values because here I am eliminating options, so I got the real values. One is for 0.809 and second one is minus 0.309. So
Yeah.
what is the fourth option?
Yeah, I'll show you the screen.
That is the answer.
Yeah. Here, the screen is visible?
Yes, Ben. So the answer is C.
Yeah, yes. So you actually have the negatives also, because when you plot it, you also plot it on the j-axis. So no need to eliminate them. Okay, so that was all for this session. So if anyone has any doubts, can ping me in. I'll be there till 8:30 in this session. So you can stay back and let me know. Thank you.
Thank you, ma'am.
Thank you.
Thank you.
Ma'am, I have two doubts.
Yeah.
Ma'am, the covariance matrix is given by that matrix variance of x, covariance of xy, 2 by 2 matrix of variance. Yes, ma'am. So, ma'am, when we take a constant out from the final matrix, then will that constant be also should be taken into account? Like in the assignment, the option 1 is the correct answer. It's coming when we take 0.75 out of the matrix.
So you're talking about this week's assignment? The current
Yes,
assignment
ma'am.
has been.
Yes, ma'am.
Okay, wait, let me share my screen. Okay, this one? Which question?
Yes.
This one?
Yes, ma'am. Sixth. So, ma'am, when I calculated the 2 by 2 matrix, that is the variance x, covariance xy, and in the second row, covariance yx and variance y. So,
Yeah.
the first option I'm getting when I'm taking out 0.75 out of the matrix, then I'm getting that one elements. So, my doubt is that we should take that constant into account or not.
You should take it.
0.75.
It's
Ma'am, but
not
no
any.
option is matching then.
Then perhaps you might have calculated the covariance wrongly. can try compute it. So how do you compute it? You cross check the formula.
Yes, ma'am.
So what did you do?
Ma'am, it's a 2 by 2 matrix of variance x. In for the first row, variance x, and then the covariance of xy. And in the second row, it's a covariance of yx and variance of y. And covariance of xy and yx are equal, so they are same.
Both of them are same. So for this question, I'll perhaps okay. There's some background activity. Okay. So I'll try doing this thing and I'll you can share your email ID. I'll share you the answer for the same.
Yes, ma'am. Ma'am, my email is PORWAL.
There's so much.
Ma'am, PORWAL Porval
Huh?
dot AYUSH
Okay, one message.
2002 @gmail.com.
Okay.
And ma'am, two more doubts.
Yeah.
Ma'am, in second question, it is given that what is the minimum bit count for an ADC needed to achieve a resolution of 50?
Yeah.
The same question that we discussed.
Yeah. Yes.
So ma'am, I have a doubt that resolution is given by the VREF upon 2 to the power n minus 1. Then why
Yes.
we are not calculating this by using that formula? Why we generated a new formula 2 to the power n equal to resolution?
So
We
it's not like that. So here you don't actually have a voltage rating, that's an input voltage rating given to you. So here they are trying to ask the minimum bit count. Where there we were trying to see that to reach what's the question was there exactly was okay, wait, I'll let you know the actual differences so that you don't confuse. So there was the minimum number of bit that was required. Okay, no. The voltage one you're saying, right? Okay, wait. Yeah. Resolution of an ADC for the input range of that. So there we are actually computing the resolution. Here what we're trying to see is like if we have this resolution given to us, what would be the minimum bit count when the voltage rating is not given to you? So that would be simple. You just compute it it's like 2 raised to n minus 2 raised to n minus 1 raised to 50.
ma'am, VREF upon 2 to the power n minus 1.
But here you don't have the voltage rating given, right?
Hmm.
So you directly uh, there's too much noise. You directly equate it.
And ma'am, in the first question, ma'am, they have used the formula VREF upon 2 to the power n. They have not taken minus 1. So is there any
Because
difference? Ma'am,
you
so
tell
is
me.
there, ma'am, is there any difference? Ma'am, because
Yeah.
ma'am, when I was taking 2 to the power n minus 1, the options were not matching. And when I
Mm-hmm.
removed the minus 1 part, and then the option matched, and A is the correct answer, 19.53 millivolt.
No. Then what's the input range given to you?
Ma'am, voltage range is given 0 to 5.
Yeah. We are actually at 5 volts, right? So it's isn't 1, 2, 3, 4, 5. At 0 volt, it would be nothing. It's just
Yes,
the
ma'am. So, yes, ma'am. So it will be 5 upon 2 to the power 8 minus 1,
no.
the
So when
resolution.
So the way that you're saying it's very right that when a particular voltage is given, we divide that particular voltage divided by 2 raised to n minus 1. So why? Because we have our bits from 0 to n number of counts. So now when we have these as 0 to n number of counts, we do it like this. But now the input voltage range is given as 0 to 5 volts. So they have considered the bit values at zeros as well. So what you have to do is that you need to neglect this particular one so that because here you have the input range from 0. So just consider the 5 because 5 minus 0 is 5 and divided by 2 raised to 8.
Yes, ma'am. And ma'am, one more doubt. That when the signal does not follow the random test, that is the number of turning points should be greater, then we can't say about the quasi-periodic and the periodicity.
Yes, we can't.
Yes, ma'am. Yes, ma'am. Okay, ma'am. Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you. Okay.